Chapter 2: Nonlinear Functions and Models. Section 2.1: Quadratic Functions. Introduction. The relationship between two quantities is often best modeled by a curved line rather than a straight line. The simplest function with the graph that is not a straight line is a quadratic function. The nonlinear functions we discuss in this chapter are the quadratic functions, exponential functions, and logarithmic functions. Quadratic function. A quadratic function of a variable x is any function that can be written in the form f of x equal to ax squared plus bx plus c, where a, b, and c are constants, with a not equal to 0. Orientation of a parabola. Any quadratic function of the form f of x equal to ax squared plus bx plus c can be graphed in, when we graph it, we get a shape of a parabola. And this parabola is either concave up when a is greater than 0, or it's concave down when a is less than 0. In sketching the graph of a parabola, you need to know 4 different features. First, you need to find the vertex of a parabola, and the vertex coordinates are given as x coordinate is given by the formula negative b over 2a, and y coordinates of the vertex is given by f negative b over 2a. Second, to determine the concavity, parabola is either concave up when a is greater than 0, and it is concave down when a is less than 0. Third, to find the y-intercept, we find y-intercept by setting x equal to 0 in the parabola equation and then solve for y, and usually y-intercept is equal to c. Fourth, to find x-intercept, we set y equal to 0 in the parabola equation and then we solve for x. We can either solve for x by factoring or solve for x by using the so-called the quadratic formula. Quadratic function shape. Every quadratic function has a parabola as its graph. All parabolas are vaguely U-shaped, and they will have a higher or the highest or lowest point that is called the vertex. Parabola may open up or down and may or may not have x-intercept, and they will have a single y-intercept always. Part 2 of sketching the parabola. To find x-intercept, if any, we can solve the quadratic equation. We set f of x equal to 0. We can either do by factoring method or maybe use quadratic formula that says x is equal to negative b plus or minus b squared minus 4ac divided by 2a. The quantity b squared minus 4ac is known as the discriminant and give us 3 types of information about x-intercept. If the discriminant is 0, there is a single x-intercept. If the discriminant is negative, there is no x-intercept. If the discriminant is positive, there are 2 x-intercept. Sketch the graph of f of x equal to x squared plus 2x minus 8 by hand. First of all, we follow the 4 steps I mentioned in the previous slides. First, we want to find the concavity of this parabola. Since a is greater than 0, the parabola is concave up. The coordinates of vertex are -1 and -9. Y-intercept is equal to the c, which is -8. X-intercept are equal to -4 and 2. This is by solving for the quadratic function x squared plus 2x minus 8 equal to 0. So when we solve for that, we get x-intercept to be -4 and 2. The graph of f of x equal to x squared plus 2x minus 8. This is the graph of that parabola we discussed in the previous slides. We can sketch it. Now see that the parabola is symmetric about the axis x equal to -1. Alien Publication Incorporated predicts that the demand equation for the sale of its latest illustrated sci-fi novel, Episode 93, Yoda vs. Alien, is Q, which is equal to -2000 P plus 150,000, where Q is the number of books it can sell each year at a price of P dollar per book. What price should Alien Publications Incorporated charge to obtain maximum revenue? A solution to example 2. The total revenue depends on the price. And in order to find the revenue function, we use the formula R is equal to P times Q. Price times the quantity of items. So substituting for Q equal to -2000 P plus 150, we multiply that by P to find the revenue function, and our revenue function become -2000 P squared plus 150,000 P. The P coordinate of the vertex is now equal to -150,000 divided by 4,000, and that gives you 37.5. Max revenue at price of 37, we plug 37 into the revenue function and we find 2.8 million. This is the solution of the problem number 2, as you can see it pictorially here. Exponential functions and models. Introduction. The quadratic functions can be used to model many nonlinear situations. However, exponential functions give better models in some applications. In population growth, radioactive decay, the growth or depreciation of financial investment. Laws of exponent. So if I have two numbers with the same base but different exponent, I can keep the base and add the exponent. If I'm dividing two numbers with the same base but different exponent, I can keep the base and just subtract the lower exponent from the upper exponent. If I have 1 over bx, 1 over b raised to power of x, this is equivalent to saying b raised to power of -x. Any number raised to power of 0 is equal to 1. When you raise a power to another power, all you are doing is you are multiplying those two powers. And if you have a number b divided by c raised to power of x, this is equivalent to saying b raised to power of x divided by c raised to power of x. Exponential functions. An exponential function has the form f of x equal to a b raised to power of x, where a and b are constants, with a not equal to 0 and b positive not equal to 1. We call b the base of the exponential function. Quick example. Let f of x be a function that is equal to 2 raised to the power of x. F of 1 is going to be 2 raised to the power of 1, that would be 2. F of negative 3 would be equal to 1/8. Let g of x equal to 20 times 3 raised to the power of x. Then g of 2, wherever I have x, I will substitute for 2. So then I have 20 times 3 raised to the power of 2, and that is equal to 180. G of negative 1, that would be equal to 20 divided by 3. Exponential functions from the numerical and graphical points of view. The following table shows values of f of x equal to 3 times 2 raised to the power of x for some values of x. Let a equal to 3, b equal to 2. So if we were to represent this in terms of a table, so when we plug in negative 3, the function is spit out 3 over 8. When we plug in negative 2, the function is spit out 3 over 4. When we plug in negative 1, the function is spit out 3 over 2. When we plug in 0, the function is spit out 3, and so forth. And when we plug in 3, the function is spit out 24. So notice that if we decrease x by 1, the y coordinate gets divided by b equal to 2. The value of y is simplified or is multiplied by b for every 1 unit increase of x. So as you can see here, every time we are moving forward, we multiply this number with 2. Example number 1. Some of the values of two functions f and g are given in the following tables. One of these functions is linear and the other is exponential. Which is which? If we look closely to the table, remember that a linear function increases or decreases by the same amount every time x increases by 1. So the value of f behaves this way. Every time x increases by 1, the value of f of x increases by 4. Therefore, f is a linear function with the slope of 4. So simply from the values that I have on the table, I can take any 2 points and find the slope, and then take another different 2 points and find the slope. If the slope is the same, that means this is a linear function. If the slope is different, then that means it's not a linear function. On the other hand, every time x increases by 1, the value of g of x is multiplied by 3. Therefore, g of x is an exponential function. So these observation, you can find them in table that we discussed in the previous slide. Example 2. In the early stages of the AIDS epidemic during the 1980s, the number of cases in the United States was increasing by about 50% every 6 months. By the start of 1983, there were approximately 1,600 AIDS cases in the United States. Assuming the exponential growth model, find a function that predicts the number of people infected t years after the start year of 1983. Use the model to estimate the number of people infected by October 1st, 1986, and also by the end of that year. Solution of example 2. At t equal to 0, January of 1983, the number of people infected by HIV epidemic is equal to 1,600, or we can call that A. every 6 months the number of cases increases by 150% of the number 6 months earlier. That is 1.5 times the number of cases 6 months earlier. Each year it increases by 1.5 squared. So when we make 1.5 squared, that would be equal to 2.2 times the number 1 year earlier. Therefore, the model is given by y is equal to 1600 times 2.25 raised to the power of t. This is the number of cases. And the number of cases after October 1st, 1986 would be equal to t equal to 3.75. Then if we plug in t equal to 3.75, then we get the number of cases be equal to 33,481. At the end of 1986, that would be when t is equal to 4, the number of cases is 41,006 cases.